Okay, this is the video showing you how to simulate heat transfer within your space module in SimScale. Okay, SimScale is a cloud-based online package. It's all completely browser-based. You don't need to install anything. So if you go to simscale.com, you will need to set up an account on this using your college email and details. And when you've done that, click Start Simulating Now. I already have an account, so we'll log in there. And I'm going to go to New Project. And I'm going to call it Space. Project description, heat transfer in a space module. Choose category energy is pretty good, or aerospace. And you can create a project from there. And all these projects, you can look up other people's projects on the public projects database attached with this. Yours will be put up there as well. That's how they make it available for free, essentially. So it's asking us to import our geometry here, and we can drag and drop that from the from our computer. So if I go to my computer where I saved that previous one from SolidWorks. I'm going to go with Rhombi Solid, and it's in SolidWorks file. And open that. And import. While that's doing that, as that imports, you can click on Create Simulation. And we're looking at convective heat transfer, so we select that and create simulation. We have some settings we have to prescribe here, and we're going to select compressible, meaning that there's variations in the density of the air as it's heated, which you need for buoyant flows, which ours is, and also radiation. We'll be looking at radiation heat transfer as well. Okay, Omega SST, the turbulence model, it's the one I found to work best, and steady state is what we want as well. So take that, and so we have our geometry there. We also need to specify the direction of gravity. We're going to specify it as being in the y direction, and so we specify acceleration due to gravity, which would be minus 9.81 meters per second squared in the y direction. That's our first setting there. Our material is air, so that's what the gas inside here that we're looking at. So we're simulating the tests that we're going to be doing on it, and in the lab. So any of these that are red, we need to set now. So the main thing that we set in this are the boundary conditions. So this is the settings mainly on the outside of here. And what we're going to do is set various heat transfer coefficients, or U values, which specify the rate at which heat has been lost. It will be lost through these. And we have that from the heat calculation sheets that we've already done. And we also need to set the rate at which heat is flowing in at the bulb on the inside. So when we do that, we just specify that as 100 watts, or a certain amount of watts per meter squared as well. So we're ready to go on to the boundary conditions. So we'll see what's given there. Each of ours is going to be a wall because they're all solid. And we're assuming that there's no loss of fluid or loss of air in or out, that it's perfectly sealed. Mightn't necessarily be the case, but it's close enough. So our U velocity is no slip. The no slip condition, the U velocity, the air sticks to the wall at all points, and its velocity is 0. And the temperature type is the one we're interested in. So we're going to select external wall heat flux first, and derived heat flux, and what it's asking for is a heat transfer coefficient. This is equivalent to a U value, watts per meter squared per Kelvin. So the rate of heat loss per meter squared per degree temperature difference. So we're going to get that from our U-value calculations. So if we look at the U-value calculation for a vertical wall, you'll recall that just for a sheet of cardboard, there's no cavity in that, so I'm going to leave that out. I'm just going to assume it's all just plain cardboard. There's no second sheet of cardboard. Specify the internal and external resistances. So we need to specify the external resistance, but we don't specify the internal resistance in this case, because that's going to be calculated as part of the solution. So the rate of heat transfer from the air to the inside of the wall is going to be calculated by the code itself. So we set that to 0. So all we're accounting for is the effect of the cardboard and heat transfer on the outside. We change RSI to 0. We get a U value of 7.14. And if you look back through the useful data sheet, you see that RSI is the only thing that varies, whether it's a wall, floor, or ceiling, wall floor or roof. That's the only thing that varies between them. So this U value of 7.14, or heat transfer coefficient in this case, is going to be the same for wall, floors, and ceilings. So we'll note that down, 7.14 watts per meter squared per Kelvin. We bring back our, so we change our heat transfer coefficient there to 7.14 watts per meter squared. Our ambient temperature, we always take that as 20 degrees, just average temperature for a room. So we have an initial boundary temperature. Well, it's going to be a steady state, so the closer we can get to what it's finally going to be, the better. Let's say it'll be slightly warmer than the ambient, so let's say 21. The radiative behavior we give as opaque. So it is opaque, it's not see-through. There's no heat transfer or radiation passing through it. And all we need to do now is select all the faces that are going to be solid cardboard face, so essentially everything except the windows. So there. I'm just going to select all of these. And if this area is blue in here as I select them, they'll start inhabiting that this box here. And I turn around. Just all the solid faces that are cardboard. If they're highlighted blue, then they're selected. And not forgetting the floor and the roof either. Now that's my first set of boundary conditions. Very similar ones though are the windows. The windows are going to be more or less the same, except they're going to have a different heat transfer coefficient. So I click on, beside boundary conditions, click on plus there, wall. Distinguish that, I'm just going to change that to windows. And so we have same settings up as far as temperature type. We go with external wall heat flux, derived heat flux. So the heat transfer coefficient will be slightly different for a window. Let's click on there, go back to our U value sheet for the window. So the window we're assuming is, you cut a hole in the cardboard and cover both sides in acetate, and so we get the resistance of acetate 0.00055 with a cavity of 6 millimeters in between it, so 0.006 meters. That has a airspace then of resistance of 0.127. And from the table, we have our second sheet there. And we said before, the code calculates the convection on the inside, so we set that equal to 0. We're only counting for the what's inside the window and the external heat transfer. That will give us a sum of all our resistances then of 0.1681, our U value of 5.95, which is significantly less than for the cardboard wall. So that comes again. So for a single sheet of cardboard, it is less thermally efficient than your double glazed windows. So 5.95 is our heat transfer coefficient. 0.95. Change our ambient temperature to 20 degrees C, and make a guess of 21 degrees C at the outset. Our radiative behavior we're going to assume is transparent, because it's transparent to Light, it's going to have a certain amount of transparency to heat as well. And so we just need to select all our windows now in order to give them the location. And so keep on selecting them. Forget so I didn't include the hole in mine, but it won't make an awful lot of difference. It'll still be a good simulation of of what's happening in the experiments. I have all my locations there. I select that. All windows. Okay, so there's one last thing I want to do. If I right-click on one of these faces down here and hide that face, then you can say I'll do the windows, hide the window as well. And now I can see the sphere representing the bulb inside. And I'm going to represent a heat flux of 100 watts going through that. So my final boundary condition, another wall, and I select my location. And we go temperature type, fixed value, turbulent heat flux in this case. Have a heat flux not of 100 watts per meter squared. If we change flux heat source to power heat source and specify the power as being 100 watts for our 100 watt light bulb. Initial boundary temperature we can specify as it's going to be pretty hot because it gets hot. So put in something like 200 degrees C, and the closer we can get that to what it'll actually be, then the more accurate or the quicker we'll get an answer. And if we go here, select all and show all. And so I'm nearly finished now, so that was a bit simpler than you might have thought. All that remains to do now is click on Simulation Runs, and without getting into any detail, I'm just going to set it off to do the calculations to create a grid, a mesh, and also solve then for the temperatures and velocities within, and we'll look at the results in a while. So if we click Start, it's going to run maybe for about 15 minutes to half an hour, depending on the how busy SimScale's computers are. So we'll leave that to run for a while. After about 2 or 3 minutes, we'll say that the mesh is finished. So we have the tick down here, and you'll see that. We'll see the mesh actually on the surface here. So what it's done is it's broken the volume down to hundreds and thousands of little subdivisions, and it solves a simplified form of the fluid equations on them. So solve them as sets of essentially hundreds of thousands of simultaneous equations, which computers can do extremely quickly, as I'm sure we're going to find out in the next while. So next it's going to start doing the actual heat transfer calculations on this. And we'll leave that to run, say maybe for about 15 or 20 minutes. After a few minutes, you'll see start giving you a progress bar down here. It says I'm about 5% through my calculation. Just scroll down through this menu on the left and click on Convergence Plots and Residuals. It shows a series of graphs. What they're plotting is the error really in each set of calculations. It solves calculations for all the components of velocity, components of turbulence, K and omega, also for pressure and heat as well, enthalpy. And these are generally going downwards then. You're on to, that means the solution is improving. with each set of calculations. So we're going to let that run. By default, it runs for about 8,000 iterations, and let that run for a while. I'll say it'll take about 10 minutes. So after the SimScale simulation is run, we'll see 2 green ticks down here. I'll say it might take up to about half an hour. And what we want to look at is solution fields to look at the results of the calculation. So if we zoom out, scroll out, zoom there, and you get the best view by taking what's called a cutting plane. And if we inverse that cutting plane, it'll show us this side of it. And we color that. We can color that according to temperature. It's probably the best. And you can see that temperature of the maximum temperature in the domain is about 613.9 degrees C, down to a minimum of about around 304 Kelvin. So it's only going to be that maximum temperature on the bulb itself. It's the air we're interested in, so let's pull this in a lot to around a maximum of 366.5. And what we're looking to see is a plume of hot air rising off the bulb, which we're seeing there. And that floats up like that, hits the top, and then cools. I'll try and show that a bit more, pull this in a bit more, and we can see that, yeah, we're definitely seeing a significant plume of hot air rising by convection off here. If I zoom in a bit as well, we can see that there's also a hot spot in the bottom here as well. So that's heat transfer by radiation to the bottom then, and by convection to the top. So we have along the roof here, and particularly on this top panel, we're seeing big temperature differences between the inside and the outside. So I would assume the bulk of the heat transfer, the most intense heat transfer, would be out through the roof and these areas here, but also out through the bottom as well. And what we want to compare with the experimental tests to do would be the average temperature over this plane here, which we can do if we click on statistics here. So cutting plane 1, the average temperature 317.9 K. Let's try changing that to degrees C. So about an average of 44.78 degrees C. So I'll make a recording of that to compare with the experimental results that we're going to do on week 5. An interesting addition to this, we'll also be able to see the flow field as well. If we click on vectors on here, and we're seeing rising column of air coming off here. We see the arrows going in this direction, spreading out, and then going back downwards, down towards the bottom. So we're seeing this continuous circulation of the air. So rising off the bulb from the heat source, hits the top, cools. It's cooling as it goes down along here, and then drops back, circulates back down to be heated again. So that's a continuous convection circulation zone. We won't see that in the experiments, but it's happening. Getting, if we look at, color that according to velocity next. Instead of velocity, put velocity here and magnitude. You can see that we can get a maximum velocity of about 0.7 meters per second. So this is natural convection, so we're not going to get high-speed velocities. Here, it's being driven purely by buoyancy, by heating of the air and reducing its density. And so we get up to 0.7 meters per second, nearly a meter per second, about 2 or 3 kph, 3 or 4 kph in fact. So significant velocities there above the bulb, and large temperature differences. And we can isolate for our designs where the heat transfer is liable to be the greatest as well, to be the largest. Okay, that's how we do the simulations for the space module.